Okay, so another method in solving linear programming problems would be the simplex method. So a simplex method is predicated on the assumption that the optimal solution will be an extreme point, and the constraint equations are reformulated as equalities by introducing what are called the slack variables. So the simplex method uses numerical methods approach in finding the optimal solution, and that is considering the extreme points, so similar with that of the corner method, okay, so in a graphical method approach. So under the simplex method, we are introducing the slack variable. So when we talk about the slack variable, that is for every constraint. Okay, so for every constraint, we are introducing one slack variable. The slack variable constitute the amount of resources, okay, so that are available and was not, or it was not used. It measures how much of a constraint resource is available. So for example, if we have a 250 hours for labor production or for production, and only 240 hours, okay, so is needed for the optimal solution, then the 10%, okay, so which is an available resource which was not used, is what we are referring as the slack variable. Okay, so if we are given a constraint, let's say for example, we have 7x sub 1 plus 11x sub 2, wherein x sub 1 and x sub 2 are the decision variables, and this constraint is less than or equal to 77. So in simplex method, we are introducing a slack variable s sub 1 that is to represent, okay, so that is to represent the amount of variables or the amount of resource or resources which will not be used. Okay, so that is the slack variable. So there are different steps in solving LP for maximization problem using simplex method. The first one is, once the LP problem was formulated, we need to develop a slack variable for its constraint equation to form the fully augmented version of the LP. Okay, so the linear programming, which consists of the objective function as well as the constraints, can be formed with the augmented LP version, by introducing the slack variable, for every given constraint. And then we create a table for the fully augmented version of the LP. We create a table by getting the coefficient of all the variables involved in the LP problem, and then decide for entering and leaving variable. So we decide for entering and leaving variable. So take note that when we say entering variable, entering variable can be taken from the objective function. Okay, so the most negative, okay, or the most negative uh, coefficient, okay, is what we are going to consider as the entering variable. Okay, so the variable in an objective function with the most negative coefficient is considered to be the entering variable. So we get that one on the row. So for the living variable, once we were able to distinguish the entering variable, we take a look at the column, okay, of the entering variable, and then we take the intercept, okay. So we take the intercept uh, by dividing the solution with that of the coefficient of the living variable. And the one which will yield the uh, smallest positive intercept, then that is considered as the living variable. So these are the succeeding steps. So we determine the pivot row, the row of the living variable, and the pivot element, the coefficient of the entering variable. And afterwards, we replace the living variable by entering variable. So divide the pivot row by the pivot element and eliminate the coefficient of the entering variable for all the rows, and we just need to repeat the steps again and again, so until there is no negative coefficient for our objective function anymore. Okay, so we know that the result is final because there are no negative coefficient remaining in the objective function row. So to better understand that, so we will be repeating the same problem. So just like what we solved, okay, so for the graphical solution. Uh, so this is the LP problem. So we have to maximize the profit of $70 times the table or number of tables. So plus $50 for the number of chairs. And the carpentry constraint, so we have 40 plus 2C, and the painting and varnishing constraint, so we have 2T plus 1C is less than 100. So using the simplex method, so we will be introducing the slack variables. So in this case, for the first constraint, which is the carpentry constraint, so we have 40, so plus 3C, and then plus S1 as for the uh, slack variable for the first constraint, and then that will be equal to 240. And then we have 2T, and then plus C, and then plus S2, and that would be equal to 100. And then for our profit, so this profit is the same as Z is equals to 70T, so plus 50C. So the solution here would be 0, so I'll be introducing Z here, and then plus 70T plus 50C is equals to 0. And we are not introducing slack variable, okay, so for positive constraints, because slack variables is only for constraints due to resources, but for the positive and or for the non-negativity constraints, so we are not introducing that one. Okay, so now we write the variables. Okay, so for the rows, so we have make it in red. So we have the Z, which is the profit, and then we have T as the number of tables, C is the number of chairs. So S1 is for the first slack variable, S2 is for the second slack variable. Then we have the solution, and we could have the, okay, we'll just start there. And then so for the first row, so the first row corresponds to the objective function Z. And then for the second row, so that one corresponds to the first slack variable, and then the second constraint is for the second slack variable. And then we write the coefficient, so coefficient of Z is 1, and then we have 70, or sorry, that should be negative. So it's because if we transpose 70T and 50C, so it should be negative. So negative 70T and negative 50C. So this should be negative 70 and negative 50. So we have 0 for S1, S2 is 0, and then the solution is 0. So for the first constraints, so we don't have Z. So then we have 40, 3C, the first slack variable is 1, S2 is 0, and then solution is 240. The second constraint, so we have 0 for the Z, and then 2T, 1C, 0 for S1, and S2 is 1. And then we have 100 for S2. And we decide now, so once we have the augmented table or the augmented matrix, so we decide for the entering variable. So entering variable, or sorry, the living variable, okay, so the living variable is the coefficient with the most negative coefficient. So in this case, so we look at the rows. So we have a negative 50 and or negative 70 and a negative 50. So negative 70 is more negative than negative 50. So therefore, this will serve as our entering variable or leaving variable. And then we decide for the leaving. This should be the entering. Okay, I'm correct. Sorry. So it should be the entering variable. So since it will replace the leaving variable, so entering variable is the most negative coefficient. And then so we take or we compute for the intercept. So for the intercept, so we take the solution, divide it with that of the entering variable column. So in this case, so we have the solution here, which is 240, and then the coefficient for the entering variable is 4. So 240 divides 4 is 60. And then we have 100. So divide it with 2, which is 50. And our leaving variable then, so will be the smallest positive. Okay, so smallest positive, 60 and 50 is 50. So therefore, S2 will become our leaving variable. Okay. So in this case, so we take the, okay, so this will be our entering, and this would be our leaving. So in this case, the row or the row of the leaving variable is what we are referring as the pivot row. And then the intersection between the entering and the leaving, so is what we are referring as the pivot element. So for pivot element, so we want to make the pivot element equal to 1. Okay? So pivot element should always be equal to 1. So to do that, so we need to manipulate the entire pivot row. So that is the third row in this case. So this is R1, this is R2, and then R3 for our pivot row. So in this case, so that will be R3. So we divide it by 2. So we divide it by 2 so to make the pivot element equal to 1. So to do that, so I'm just going to rewrite the T, C, S1, S2, the solution, and Z, S1. So since our entering variable is T, so the leaving variable S2 will be replaced by the entering variable. So instead of writing S2 here, so we will write T there. So T replacement. And I'm just going to copy. So 1, negative 70, negative 50, 0, 0, 0. 0, 4, 3, 1, 0, 240. Then we have 60 there. So we divide, or we don't need this one. So we divide uh, the entire R3, so by 2. So I'll start with the 0. So 0 divides 2 is 0. Then 2 divides 2 is 1. So 1 divides 2 is 1 half. And 0 divides 2 is 0. So 1 divides 2 is 1 half. So 100 divided 2 is 50. So after making our pivot element equal to 1, so we have to make all the rows, okay, so above the pivot element, so to be 0. Okay, so we want to make this, okay, so since this is our pivot row, so I want to make the negative 70 and positive 4 equal to 0. So to do that, so what we're going to do is so this is R1, R2, and R3. So our reference is, so I'll have R1. So R1, then minus, so our formula would be the row that we are changing to 0. Okay, so minus the coefficient, which is negative 70. So minus negative 70, so that would make it plus 70. And then the pivot row, which is R3. The second one, we have R2 minus 4. Okay, so minus positive 4, so that is minus 4. And then R3. Okay, so I'll rewrite that. So ZTC S1 S2 solution. So Z S1 T. So R1, R2, R3. So I'm just going to copy my pivot row. So 0, 1, 1 half, 0, 1 half, and 50. So I'm going to follow this formula. So in this case, my R1 is, this is R1, so which is 1. So it's just like R1 plus 70, that is 1 plus 70, our R3 is 0. So using this row, okay, the 0, our R1, the coefficient of R1 there is 1 plus 70, so times R3, the coefficient of R3 is 0. So that makes it equal to 1. So this is 1. And then for the one below, so we have R2. R2 is 0. So plus 70. And then R3 is 0 as well. So thus this would be equal to 0. So that is the same thing that we're going to do for the rest of the rows. So we have negative 70 plus 70 times 1. So that is 0. And then 4 for R2 minus 4. R3 is 1. So 4 minus 4, that makes it 0. Then we have negative 50 plus 70 times 1 half. So negative 50. 70 times 1 half is 35. Negative 50 plus 35 is negative 15. And then we have for this one, so 3 minus 4 times 1 half. So 4 times 1 half, so following this formula, so 4 times 1 half is it's 2. And then we have R2, which is 3. So that makes it 3 minus 2. 3 minus 2, it's 1. Okay. So 3 minus 2 is 1. And then for our S1, so S1 is 0, our R3 is 0. So therefore this is 0. S and then we have for R2 is 1 minus R3 is 0. So 1 minus 0 is 1. So for S2, so I'll start with this one. So 0 plus 70 times 1 half. So 0, 70 times 1 half, that is 35. And then this one is 0 minus 4 times 1 half. So 0 minus 4 times 1 half is negative 2. And for our solution, so 0 for R1 plus 70 times 50. So 70 times 50 is 3,500. Then we have 240 minus 4 times 50. So 240 minus 4 times 50. 4 times 50 is 200. So 240 minus 200, that is 40. So are we going to stop now? Okay, so we have to check our objective function. Is there still a negative coefficient? Okay, we still have a negative coefficient. So which is for the variable c. So variable c now will become our entering variable. So to find the living variable, so we need to find the intercept. So the intercept here then, so would be the solution. So in this case, so that will be the solution, which is 40 divided by 1. So which is 40. The other one is 50 divided by 1 half. So which is 100. And obviously, so 40 is the smallest positive. Therefore, S1 so will become our living variable. So living variable for S1. And thus, so this would become our pivot row. And this is our pivot column. And this is our pivot element. The difference this time, so we don't need to divide it by 2. So since our pivot element is already 1, so thus we proceed with making the upper row and the lower row equal to 0. Okay, so to do that, so this is our formula. So that would be R1, the one that we are manipulating. So minus negative 15 is plus 15. And then our pivot row, which is R2. So for the second one, we have 1 half. So that is R3. And then minus 1 half. Our pivot row is R2. So so this would be Z and T, C, S1, S2, the solution. So this time, the living variable S1 so will now be replaced by C, and this would be by T. And we use this formula. So by the way, we copy our pivot column or pivot row, which is 0, 0, 1, 1, negative 2, 40. So we follow this formula. So I'll finish the entire row. So R1 is 1, R2 is 0, so 1 plus 0 is 1. R1 is 0, R2 is 0, so therefore that is 0. So R1 is negative 15 plus 15 times 1. That's negative 15 plus 15, which is 0. Then 0, S1 is 0. R1 is 0 plus 15. R2 is 1. So 0 plus 15, that will be 15. And then we have 35 for R1. And then 15 times negative 2 is negative 30. So 35 minus 30, that is 5. Then for our solution, so we have 35 plus 15 times 40. So 15 times 40 is 400 plus 200, 600. So 35 plus 600 is 4,100. Okay, so that's our first row. So for the third row, so we have R3, so which is 0, and then minus 1 half R2 is 0. So 0 and 0 is 0. We have R3 is 1 minus 1 half times 0, that's still 1. And then 1 half minus 1 half times 1 is 0. So 1 half minus 1 half is 0. Then we have R3, which is 0 minus 1 half times 1. So we're talking about this. So 0 minus 1 half times 1. 0 minus 1 half times 1 is negative 1 half. And then we have 1 half minus 1 half times negative 2 is positive 1. Correct? Negative 2 times 1 half. Negative 2 times 1 half is positive 1. Plus 1 half is 3 halves. And then, so we have 50 minus 1 half times R2. R2 is 40, that makes it 20. So 50 minus 20, that is 30. So now, if we are going to rewrite this, it would appear that, okay, so excluding, okay, so without considering the slack variables, so we could write that this one. So Z is equal to $4,100. And for C is equal to 40. And T is equals to 30. So as you can see here, so we need to produce 40 chairs and 30 tables to yield a maximum profit of $4,100. So given our z, so to be equal to 70t plus 50c. So will that be the same? So 70t is 30. So plus 50c is 40. So z is 21. So plus 2000. So c is 4100. So which is correct. So therefore, so this will be our decision. So we need to produce 40 chairs and 30 tables. Okay, so to yield a maximum profit of 4,100. And that is how we do the simplex method. So this is just to give us an idea, especially for non-IE major. Okay, so this is how we do it manually. Okay, although on our succeeding example, so we will be using, okay, so applications. So we'll introduce first using Excel, and then we have the Excel solver, and then we have other applications as well, the QM solver, in solving. Okay, so in solving linear programming problems, what is needed here is we need to understand how to construct, okay, an LP, how to formulate a linear programming model, and then afterwards, so once we know how to construct LP, so we can use software already. Okay, so in solving or in making a final decision. So next meeting, so we'll try to do the minimization problem. So using, or I'll introduce different solver, okay, so to find solutions for linear programming problems.